Okay, so TRO Chapter 3, Section 9. TRO Chapter 3, Section 9, we're going to be talking about getting chemical formulas from experimental data. What? We're going to get a chemical formula from the reaction itself? I thought it was the other way around. Okay, so we've got to have we'll spend some time talking about this. And we're going to find we've got real interesting, clever ways to get chemical formulas. Then we're going to calculate chemical formulas. And that'll mean more as the video unfolds. And finally, combustion analysis. All right, so chemical formulas. Let's remember what these are about. First of all, empirical formulas. Remember that we had empirical formulas, and the empirical formula was, you really should tell me, I'd like to ask you a tight question. X, N, Y, M, where N and M were a ratio of small whole numbers. Actually, that was really the ratio of the smallest whole numbers, right? Possible. That was empirical formulas. We dealt with that a good bit already. We're going to deal with it even more now. So empirical formulas is one kind of formula. And then there's other formulas too. So that's, which I've got enough slide coming up. For a second there, I was thinking what we were doing with that. All right, so first of all, let's consider this question here. This is something that could be meant by experimental. So again, the title of the section is determining a chemical formula from experimental data. Okay, so suppose that we get this, and I'm reading on page 103. Suppose we decompose a sample of blank. All right, suppose we decompose a sample of water, not knowing what water is made of, okay? Suppose we decompose a sample of water in the laboratory and it produces 0.857 grams of hydrogen and 6.86 grams of oxygen. All right, so how do we determine an empirical formula from these data? So what I'm going to do is, I just read that page 103, the first full paragraph to you. But what I have laid out here is a way that I'm going to solve this by organizing my data. Okay, so I know this. Going back to an empirical formula is X and Y and an M, where these were a small whole number ratio of what? Of the atoms in the molecule, right? So if we can find how many moles of X there are for how many ever moles of Y, that's going to be N to M. Really, the question is going to ultimately be, what are the moles of each of these guys, right? Okay, in order to get that, I can get that from the mass. If I know what this is, right, that's H2, I know the mass of it, so I'm going to say the formula weight in grams per mole. We did this in a previous section here, right? Formula weight, actually I think I've got that on the next slide. Let's keep it like this. The formula weight, and then from the formula weight, I'm going to get the moles, right? Okay, so what's the formula weight of H2? Well, H, according to the periodic table that you've got in front of you, is 1.008 grams per mole. That's what H is, right? So H2 is going to be 2.016 grams per mole, right? It's 2 times that. Oxygen is 16.00 grams per mole. Can you read my writing? O2 then is going to be what? 32.00 grams per mole, right? Okay. So this is 2.016 and this is 32.00. Notice this, I'm keeping I want you to notice how I'm laying out my problems. And I do this so that I don't lose things. And so I always have sort of an awareness of where I am. I'm aligning my equal signs. I'm going from mass to formula weight to moles. And I know, it looks like if I take grams and divide it by grams per mole, the grams are going to cross off, right? You see that? Grams and grams per mole. So this is going to be 0.857. Got to do this with my calculator here. 0.857 divided by 2.016, 4.393. 4.39335, and so on. Okay? And 6.86 divided by 32 is, something's not right about this. 6.86 divided by 32. I think I've got something wrong here. 0.214375. 6.86 divided by 32, that's correct. But I gotta go back here and look at my 0.857 divided by 2.016 is equal to 0.42. I don't know how I got this number here a second ago, but this isn't right. These numbers were just very different. That's how I said something must be wrong. 0.4253. Okay? All right, so what that means is that whatever water is, it's got a ratio of moles of water from this to this. Can you see this? Whatever this, when the water breaks down, it gives hydrogen and oxygen. And the question is, what are the ratio, right? So that's what the question of empirical formula is. What is the ratio between those two, N and M? So in order to find that ratio, what I'm going to do is I'm going to take, let's take the hydrogen to oxygen ratio. The moles, we did this before in chapter 1, is going to equal to 0.4253 over 0.214375. Okay, now in order to find the smallest whole number ratio, I divide both numbers by the smallest of the two. And which of these is smaller? It's 0.214, right? So let's go 0.214375. Divide this one by the same, 14375. And this is going to equal something over 1, right? Because these two are the same number. So what is 0.425 divided by 0.214375? Comes out to 1.9. Okay, 1.9839. Okay, can you see what this number is? If this is a small whole number ratio, if it's a small whole number ratio, what number is that? It's 1. What number is that? It's 2. Okay, and so we say, aha, the formula of water then is going to be the moles of hydrogen here is 2, and the moles, right, because that's the moles of hydrogen, and the moles of oxygen is 1, which we leave blank. And so that is the formula for water based on what I have here. Okay, we're going to do this more with a couple more examples. I think on the next slide I've got. I set myself up for that, right? Okay. All right, so let's do an example, 3.15, and this is on page 103 in your textbook. Page 103. All right. A compound containing nitrogen and oxygen is decomposed in the laboratory and produces 25. So we do the same thing here. Okay, so it's nitrogen, M, oxygen, N, right, is decomposed into nitrogen and oxygen. Watch this, nitrogen and oxygen. Now it turns out nitrogen presents in nature as diatomic molecule, and so does that. Although it turns out if you get that wrong, it's not really going to matter. All right. So mass, watch this, in grams. I'm setting this up as a table where this is a column heading, this is a column heading, this is a column heading. Can you see that? The mass in grams of nitrogen, 24.5, and mass in grams of oxygen is 70.0. Okay? So let's do this now. The formula weight in grams per mole. The formula weight of nitrogen gas. I'm going to save some time here. Look at the periodic table real quickly. Nitrogen. I guess I should write this out. Some of you aren't comfortable with it yet, maybe. Nitrogen is 14.01, and so N2 is equal to 28.02. Okay, 28.02, and oxygen is 16.00, and so O2 is going to be 32.00. Okay, and so the moles, right? You can see if I take grams and divide by grams per mole, the grams will cross off and I'll be left with moles. So I'm going to take this and divide it by that. And that comes out to be 24.5 divided by 28, 0.875, 0.875, and oxygen is 70 divided by 32. Comes out to be 2.1875. 2.1875. And so it looks like the compound is nitrogen 0.875 to oxygen, which is 2.1875. And recall that to get the smallest whole number ratios, we are going to just do the moles of nitrogen over the moles of oxygen. Doesn't matter which we do, right? 0.875. I think I did the smallest one in the bottom last time. We'll do it on top this time. And the moles of oxygen, 2.1875. And so we divide both by the smallest number, which is the smallest number, top or bottom? At the top is, right? 0.875. 0.875. This is going to be 1 on top now. And what is 2.875 divided by 0.875? 2.5. Okay? So if that's the case, what is this smallest whole number ratio? Okay? This goes to 1. I can't do that. 2.5, which is really 5 halves, right? Watch this. Which is the same thing as 2 or 5. Agreed? You know how you do that? Remember that from fractions? You take the numerator, the denominator of the, let's see, yeah, the denominator of the denominator and put it up in the numerator? Okay. All right, so this is a fraction issue. I think I'm going to leave this off this video here, how I did that. If you've got a question about that, then please do come to me. So it looks like the formula for this is N2O5. Okay? So that we've calculated, again, in review, what we did was we took the amounts of the masses we got from some experiment. We didn't know what this was. We calculated the masses that we got from this experiment. And when we did that, we calculated how many moles were there, right? And then we found the smallest whole number ratio of those moles, okay? So I think we've got another example here on page 103. And let me move on here to example 3.16. Yep, this is also page 103. Oops, gotta go back. Page 103 in your text. Okay, so all right, another complicator here now. A laboratory analysis of aspirin determined the following mass percent composition: 60%. Wow. Okay, so this is not chemistry, by the way. This is ratios and percents. But let's do this. Let's say if we have where are we here? It's C. Do you mind if I just make something up? CNHMO. Oh, I don't know. Running out of letters there. X is going to give us carbon, hydrogen, and oxygen, right? Turns out it doesn't really matter how they show up in nature. I'm just going to call them that. The mass of each of these in grams. And moles in moles. Okay, didn't really line my equal signs up very nicely, but you can see that I'm setting up a table just like I did before, right? Okay, so I guess there's one trick I'm going to do here. We're not told how many grams there are, so I'm going to do, this is a trick. Assume a total of 100 grams. Oh wow, if that's true, how many grams of carbon do I have here? 60%, or 60 grams. How many grams of hydrogen do I have? 4.48. And how many grams of oxygen? You see it? 35.52. This is the trick. Assume, by the way, this is not common, this is not unique to chemistry or physics. This is, when you get percents, this is something you can assume. It's going to save you, it's going to be a little bit of a shortcut for you in really different kinds of games that we play in the future. Okay, so what's the formula weight of carbon? According to the periodic table, which you have in front of you, is 12.01. Hydrogen's 1.008. And oxygen is 16.00. Okay, so that being the case, we're going to calculate the number of moles like we did before. 60 divided by 12. I can do that in my head, but I'm going to pretend like I can. That's 5. 60 divided by 12.01 is 4.9958. 4.9958. Okay. 4.48 divided by 1.008 is 4.444. Okay, and oxygen .52 divided by 16 is going to equal 2.22. Oh, it's just 2.22. Okay. Just 2.22. All right. So now, again, what we do, I'm going to set up, instead of setting up a ratio, because, you know, before we were doing like N of, we did nitrogen over N of oxygen, right? Well, we can't do N of carbon over N of hydrogen over N, because we're not used to seeing fractions like that, okay? So let's set something up different. Let me just make up a new column, N prime. This is also moles, but it's going to be reduced mole, okay? I'm going to take each of these and divide them by the smallest number. And so I can see that the smallest number is 2.22. That's going to go to 1. I can see that's going to go to 2. Can you see that 4.44 divided by 2.22, 4.444 divided by 2.22 is going to be very close to 2. Agreed? Okay, but what I can't see is 4.98. Is that 9958? 9958 divided by, okay, and this goes to 2.2504. 2.2504. Okay, so this is a little bit tricky. What kind of small whole number ratio does this look like? This looks like 1, that looks like 2, and this looks like what? Can you see a quarter there? Because it's 0.25? All right, so I'm going to go with a third column here, or a third row, I should say. This looks like this is going to be 2 1/4, which goes to be 9/4. This goes to be 2. How many fourths is that? I guess that's 8/4, right? How many fourths is this? 4/4? Okay, uh-oh. I'm going to do a third column just because I can do this all day, right? We're looking for numbers that are clean. So what's the small whole number ratios here? Looks like it's 9, to 8 to 4. All right. By the way, these numbers up here are a 9 to 8 to 4 ratio. Okay. So everything I did below that is just simplifying it down. So, all right. That's page 103. It finishes on page 104. And so now that's it for obtaining experimental formula from finding the empirical formula from experimental data. Now we're going to go on to calculating molecular formulas from empirical formulas. All right. So in order to do that, let me remind you, this is a figure that we had. I don't remember now. This was in section 3.3 or 3.2, but we talked about in that section benzene. We didn't really talk much about it, but we looked at it, okay? So in benzene, this was the structural formula. And the structural formula shows us all the atoms and all the bonds, right? So I've got carbon, it's bonded to another carbon, bonded to another carbon, and bonded to a hydrogen, another one here, which is the similar bonding, right? Okay, so that's a structural formula. You remember what the empirical formula was? Of course you do. It's the smallest whole number ratio. So it looks like I've got here my empirical formula and my molecular formula. Let's do the molecular formula first. How many carbons do I have here? 6. How many hydrogens? 6. Okay, so what's the smallest whole number ratio between those? It's just CH. Okay, remember why this is a good example of, or rather a good reminder of why we use benzene, because it's a great example. CH could be a lot of different things, right? But with the molecular formula, 6 carbons and 6 hydrogens, there are several ways to bond those together, benzene being one of them, but it certainly narrows the field. Certainly much more information than just simply the empirical formula, which is CH. Okay, so what we're going to do now is we're going to say, what's the empirical formula molar mass? Well, the molar mass is going to be 6 times carbon plus 6 times hydrogen, right? Carbon is 12.01, looking at the periodic table. This is 1.008, right? And so let's calculate that. 6 times 1.008. .048. I guess I should have been able to do that in our head. 6.048. 6 times 12 is 72.06. This looks like this is going to come out to be about 78. Plus 72.06 comes out to be, just 1 second here, plus 72.06 comes out to be 72.108. 78.108. This is grams per mole, right? So we've done molar mass before. What's the empirical formula molar mass? Oh, wow, okay. So the empirical formula is CH. And so the empirical formula molar mass must be simply 1 times carbon, 0.01, plus 1 times 1.008. Okay? So this turns out to be, well, 13, right? 13.018, okay? Grams per mole. All right, by the way, I'm clearly not obeying my sig figs rule here. If I was, I would write this out. You tell me, if this was my final answer, what would I write this out as? Pause the video and fill in the box. Okay, let me suppose that you paused the video. Since we're adding, then we're going to be restricted to the 100ths place. So this is the last digit we can report, 13.02, right? Because it rounds up, grams per mole. Okay, but we're not. This isn't our final answer right now. Right now, all we're doing is trying to figure out what the molecular formula is. So we're going to keep all our digits till the very end. So your empirical formula molar mass is simply the molar mass if those were the only atoms you had. Your molar mass is going to be the full thing, right? So if we're trying to figure out what the molecular formula is from the empirical formula, what we can do is we can take, suppose that you knew that benzene had a formula mass, suppose you knew, this was given, okay? If that was given, grams per mole, and then you found the empirical formula, molar mass, getting a little lazy here, empirical formula, molar mass, okay? And if you found that was 13, watch this now, 0.18, what you would do is you would take those and you would divide it. You would say, whatever the molecular formula is, it must be a multiple of this, right? Well, we know what the molecular formula is for this example because we're looking at it. But in these kinds of questions, you won't be given that. You'll see it. We'll do an example here in just a moment. So let's take that number. And divide. Let's take 78.108 and divide it by 13.018. And we'll find, wow, okay. Well, of course, I guess we'd get exactly 6. This goes to exactly 6. Well, that's a lousy looking 6, right? All right, if that's true, now we know that the molecular formula is equal to the empirical formula times 6, right? So if the empirical formula is CH, then CH times 6 is going to equal C6H6, okay? All right, so now granted, this is a little bit of a, this is going to be challenging to some of you because we knew what benzene was before we even started, but that's the thought process we're going down. Now let's look at an example. 3.17, this is on page 105. Page 105, and we're going to do this now. Butadiene is a main component in the smell and taste of butter and cheese. Okay, it contains the elements carbon, hydrogen, and oxygen. The empirical formula of butadiene is such and such. All right, so we're given the empirical formula here. Its molar mass is such and such. We can figure out a very clever way to figure that out. All right, determine its molecular formula. So we know this, that the molecular formula is equal to the empirical formula times some number, right? So the molar mass is 86.09. Okay, let's find the empirical formula of molar mass real quickly here, okay? That's going to be 2 times carbon plus 3 times hydrogen plus 1 times oxygen, right? 2, 3, and 1. Okay, carbon's 12.01. Hydrogen's 1.008. And oxygen 16.00. Okay, so let's do that. The empirical formula molar mass then, 2 times 12.01 plus 3 times 1.008 plus 16. 43.044. 43.044 grams per mole. I can already see that's half of that, right? Okay, but the empirical formula molar mass is equal to, watch this now, 43.044 grams per mole. I can see that that's 2. Can you see it? 86 divided by 43 is 2. Okay? So the molecular formula is equal to the empirical formula times 2. So the empirical formula is C2H3O. If we multiply that by 2, we get C what? You tell me. Pause the video here and write that out. Especially if you feel lost at this point, you really should write that out. Okay, let me suppose you pause it. 4H6O2. Wow. Lovely. And that's the answer. Okay? And you're going to get something like that, perhaps, on a quiz or exam, and you're going to be so thankful when it comes out to be that clean. By the way, can you see why I'm not worried about sig figs in this conversation? We can always do the sig figs issue, but it turns out it makes no difference here because we know that the molecular formulas and empirical formulas are restricted to small whole number ratios. Okay? So now in the last, I think, the last super topic in section 9, which is a big one, is combustion analysis. Combustion, what? Okay, combustion analysis. So what we're going to do is we're going to analyze these compounds by burning them. That's what combustion analysis is. So here's what we got. This is very clever. We take a sample. We're not going to do it personally. We're going to get the results from the scientists who did it. And we're going to analyze the results. We take some sample. Okay, it's in here. You pump oxygen through here, an unknown amount of oxygen. And when you do that, when you pump this oxygen through here, you're going to find out how much water is formed, right? And then the sample is going to keep pushing through here, and you're going to find out how much carbon dioxide was formed. Okay? So, if you have an unknown amount of oxygen, as much as needed, what does this tell you? That tells you how much hydrogen was in the sample. Can you see that? Because we're pumping oxygen through there and bringing it. This tells how much hydrogen was in the sample. And when we look at this, what does this tell us? It tells us how much carbon was in the sample. Okay? And then we've got other substances not absorbed. So basically, combustion analysis is going to tell us how much hydrogen and how much carbon is in a particular sample. Okay, so let's use let's see how this is going to present on a quiz or exam. Upon combustion, some compound, right? Some compound containing it contains only carbon and hydrogen. All right, so if it contains only carbon and hydrogen, you've got CnHm, right? We're combusting it, so we're combining it with oxygen, produces carbon dioxide plus water. Okay. All right. So, and we're given these masses, as always. This is a very familiar form to us. And we're always shooting for moles, right? Might as well go ahead and write it out. We know what we're going for. So it turns out this gives us 1.83 grams of carbon dioxide, 0.901 grams of water, right? Okay, now this is of the compound. What I'm going to do is I'm going to set up another table over here, or rather another extension of my table, carbon and hydrogen. All right, we'll figure out we'll see what that means in a minute. So first of all, the formula weight of carbon dioxide. So carbon dioxide, I'm going to do it up here. Can I? No, I'm going to do it over here. Is equal to 1 times carbon plus 2 times oxygen. You remember writing 12.01, 16, 12.01 plus 32, which is going to be 44.01. 44.01. Now water is going to be 2 times hydrogen plus 1 times oxygen, which is equal 1.008 plus 16, which is equal to 2.016 plus 16, which is equal to 18.016. 18.016, okay? Now to find the moles of those, of course, we've done this a few times now. We're going to keep doing it. It's 1.83 divided by 44.01, which gives me 0.04158. I'm going to do 4 sig figs here. Okay, and the moles of water is 0.901 divided by 18.016. which is 0.05, 0.0500111. Okay, now we want to know how many carbons and hydrogens were in there. Well, I don't know how many carbons were in there, but I know how much CO2 was in there. So what I got to do now is I got to say, I'm looking for moles of carbon, right? See where I'm going with this? Okay, how many moles of carbon for every mole of CO2? I had 0.04158 moles of that, right? These guys cross off. I'm left with carbon. But it was a 1-to-1 ratio. So it looks like I'm going to have 0.04158 moles of carbon, right? But now if I'm looking for the moles of hydrogen, it's not a 1-to-1 ratio. That's 2, right? I'm looking for moles of hydrogen because that was my question, right? N and M. Moles of hydrogen. I've already figured out moles of water, right? So I'm going to calculate, that looks like this is a 2-to-1 ratio. And this was 0.050111. Okay, so this times 2, then, these cross off. Left with moles of hydrogen. Beautiful. 111 times 2 is equal to, I guess we could have done that in our head. I wasn't really thinking that clearly. 0.1000 and a bunch of 2's. Okay? That's how many moles of hydrogen we have. All right. So now what we need to do is we need to find the ratio of these. Okay? I've run out of space here. So what I'm going to do is I'm going to find another space in my paper. Extra work. And I'm going to say the moles of, I'm going to put the bigger one on top. The big one on top, okay? The moles of hydrogen over the moles of carbon is equal to 0.1000222 divided by 0.04158. Sorry for the messy handwriting. I'm going to divide those now. Divided by 0.04158. Divide both of them by the let's see, the smaller of the two. And so it looks like I'm going to get 2.4 over 1. All right? So what fraction does this look like? 2.4 over 1. This looks like it's fifths, right? 0.4 is fifths. And so how many fifths would that be? That would be 10, 14. That'd be 14 fifths, right? No, it wouldn't be. 12 fifths. 12 fifths and 5 fifths, right? So what's the ratio? Looks like it goes to BC5H12. Can you see that? Hydrogen's is 12, carbon's is 5. Wow. Okay, that's a beast. All right, but we did this in very small steps, right? We took, first thing we did was we took the masses which we were given and we calculated the moles. And we did that via formula weight. That's the first thing we did. Oh, gosh. Oh, yeah. And then after that, we figured out how many carbons were in there and how many hydrogens were in there. So this is step 1. Step 1. Here's step 2. Step 2. And then we just reduced. Right. And the reduction was, this is a ratio rule which we played in, I don't know, middle school, maybe elementary school, but it's been a while, so it's going to scare some people. All right, let's do one final example and we'll be done with this section. Well, this was a beast, wasn't it? All right, upon combustion, a compound containing only carbon and hydrogen produces this many grams of such and such. All right. Okay, so again, we've got a similar issue here. It's only got carbon and hydrogen in it, and we're adding oxygen. It's going to produce carbon dioxide and water. Leaving myself some space. Remember, I'm going to be doing this, carbon and hydrogen, ultimately. Okay, so the mass in grams, the formula weight in grams per mole, and moles, right? That's what I'm calculating. Okay, so carbon dioxide is 1.60. Water is 0.819. I just calculated this on a previous page. If you don't mind, I'm going to go ahead and say it. It's 44.01, and this is 18.016, right? And so the moles of carbon dioxide is going to be 1.6 divided by 44.01 gives me 0.0363. That's a bunch of digits there. Just a second here. 0.036355. Okay. And what is water? You should be doing this. 0.819 divided by 18.016 is 0.05. I'm sorry, 0.045459. 0.0454. I better round that up. 6. Okay. All right. So how many moles of carbon do we have for every mole of carbon dioxide? Can you see it's 1 to 1? So that's going to be 0.03636. Okay. And what about hydrogen to water? It's 2 to 1, which we demonstrated on the previous slide. It's rather 2 to 1. So for every mole of this, we've got 2 of that. This is going to come out to be 0.9 something, right? Times 2. 9092. 9092. Okay. And so the ratio then is, let's go with the smaller one on the bottom. It looks to be hydrogen over carbon. 0.09092. 0.03636. I can't tell what that is. Divided by 0.0363. I'm going to put the extra digits in there. 355. Wow, 2.5. Huh, did not see that coming. 2.5. So this appears to be 2.5 over 1 because I divided both of them by the smaller number, right? And I can see that this is 5 halves over 1, which is 5 halves. Okay? And so that means that carbon is 2 and hydrogen is 5. Okay. All right, so that is the answer. But you know what's funny? In the one in your book says it has carbon, hydrogen, and oxygen in it. What? This is not same example. On page 106. What's the difference? Okay, it's almost the same, but it's not quite the same. All right, so either way, this works fine. We can do the example that's in your book also if you like. All right, that's a lot of work. You may want to practice these problems and go through this video again. Best wishes.